All right, in this lesson we're actually going to be looking at solving equations. We're going to start off with solving exponential equations. And there's two types. The first type is what we call matching bases. It would be, for example, if you had something like 3 to the 17th equal 3 to the 2x minus 7th. Notice that the bases of those exponents are matching. So that means, if you think about it logically, if the bases are matching, then the exponents must be equal. So that means that 17 must equal 2x minus 7 because the bases are identical. Now you have a very easy equation to solve. We would just add the 7 and then divide by 2. Now, one thing that's really nice about exponential equations is think about the possibilities of your exponent, or the input for an exponential function. It was all real numbers. So we don't really have anything restricted as far as that input into the exponent. So this would be a fine answer. But what if they weren't matching to begin with? Well, one option is to see if they could match. Is there any way we could rewrite 8 as a power of 2? Well, there is. 8 is really 2 cubed. So let's leave the left side like it is, 2 to the 5th. And on this side, I'm going to rewrite 8 as 2 cubed. It's still to the x plus 1 power. Now, there was a rule about if you have power to another power. I believe the rule was you multiply. So the next step, we're going to multiply those exponents. Now the left side's still the same, 2 to the 5th. But if I take 3 times the exponent x plus 1, it has to multiply times all of that. I would get 2 to the 3x plus 3, because it multiplies to both the x and the 1. Now I've got the same situation I had up here. We have matching bases. Therefore, the exponents must be equal. And now we have a simple equation to solve. Subtract the 3 and divide by the 3 in front of the x. And we're done. Let's do a little bit harder one. That's 81 to the 3 minus x equals 1/3 to the 5x minus 6. We're doing it a lot harder. So let's think about how we can rewrite 81 as a power of 3 and 1/3 as a power of 3. So if I come off to the side, I know that 81 is really 3 to the 4th. 3 to what power would give me 1/3? Well, that was to the negative 1. So if we rewrite them as powers of 3, 81 can be rewritten as 3 to the 4th power. And then the exponent was 3 minus x. On the right side, 1/3 can be rewritten as 3 to the negative 1 to the 5x minus 6. Now, again, like what we did up here, when we have a power to a power, we're going to multiply exponents. So here we've got to multiply the 4 times all of the 3 minus x. So I get 3 to the 12 minus 4x. I've got to distribute that 4. Equals 3 to the When I distribute the negative 1 to 5x is negative 5x, and negative 1 times a negative 6 is a positive 6. Now remember what we said, matching bases mean that the exponents have to be the same. So now I have 12 minus 4x equals negative 5x plus 6. I'm going to add 5x to both sides, get my x's all together, subtract 12, and I get x equals negative 6, which is okay. Remember again what we said about exponentials. The domain was all real numbers, so all of it's okay. Type 2. If you have an equation with, I'm trying to think how I want to write this. Without matching bases. There's two ways to do it. And it depends on what you have. So, what if I had, this I guess would be example number 4, 3 to the x equals 17. It's still an exponential equation. Our variable is in the exponent. Well, one way I can do this is, since the variable's in the exponent and it's only on one side, one way I can approach this problem is to rewrite as a logarithm. That's why we did so much practice rewriting. Remember how our logarithm and our exponential were related. This base gives me the base of my logarithm. So this would be log base 3 of 17 equals the exponent, so equals x. Now that is a perfectly good answer. But what if we were needing to use it for something else and we wanted to actually find the decimal of that? Well, I don't know what that would be. I could kind of estimate. 3 squared is 9, and 3 cubed is 27, so it's going to be between 2 and a 3, but that doesn't give me a good estimate or approximation. Remember what we learned last time. There's a way we could put this in the calculator. We could take log of 17 divided by log of 3. And if I had a calculator handy, log of 17, close parentheses, divided by log of 3, and I get 2.58. It was right between 2 and 3, so we were right on that estimate. That is one way to approach that problem. I want to show you another way as well. The other way, let's rewrite the problem. The other way to do this is kind of nifty. What if we take the log of both sides? Because remember, if you do something to one side, you have to do it to the other side, and vice versa. So, if I take the log of both sides, that would give me the log of 3 to the x equals the log of 17. Oh, I still don't like that exponent being up there. Oh, but remember that rule about how we could undo a logarithm or unpack it, expand it? An exponent could go down in front of a logarithm. So if I rewrote that, it'd be x times the log of 3 equals log of 17. Now, log of 3 is just a number. If I put it in a calculator, I will get a number. So it's just a number times x. So to undo it, I can divide both sides by the log of 3. And I get x equals the log of 17 divided by the log of 3. I get the same answer. Exactly the same answer. So both methods work well. It just depends on which one you want to do. So let's do another one, kind of like that. This would be number 5. What if I had, trying to find a good example. Ooh, okay. What if we had some other stuff up in the exponent? So 3 to the x plus 2 equals 2. We could do it either way. We could rewrite it, or we could take the log of both sides. So let's look at each way. If we do the rewrite method, this would be rewritten as a logarithm base 3 of 2 equals the exponent x plus 2. I'm going to switch their sides. Let's rewrite that as x plus 2 equals log base 3 of 2. I'm feeling like I want to do that. Now to solve for x, you would subtract 2 from both sides. Now if I wanted to put it in the calculator, and I would get negative 1.369. So that's one way to do it. The other way was to take the log of both sides. So I would have the log of 3 to the x plus 2 equals the log of 2. Remember, exponents can come down in front of a logarithm. So I would have x plus 2 times the log of 3 equals the log of 2. Again, log of 3 is just a number, so I can divide both sides by it. So now I have x plus 2 equals the log of 2 divided by the log of 3, which would be x equals the log of 2 divided by the log of 3 minus 2, which is exactly what we got over there. So it would end up being the same decimal. Both ways work. It's just going to be whichever one is going to work best for you in that situation. Now, what if there's some other stuff around it? Not just more stuff in the exponent. What if I have 3 times 4.5 to the x plus 1 equals 13? Well, first off, on all of these, we had the base and the exponent, the power, all by itself. So here, we would like to get this all by itself, and then we can make our decision on which route we want to go. So let's start by subtracting 1 from both sides. It's going to give me 3 times 4.5 to the x equals 12. Divide both sides by 3, and you get 4.5 to the x equals 4. From here, I honestly think rewriting is the easier way, but it will be up to you. if you would like to rewrite it, you would get x equals log base 4.5 of 4. X equals log of 4 divided by log of 4.5, which gives me approximately, I believe, 0.921. Same thing, though, would happen if I took the log of both sides. If I took the log of both sides, I'd get the log of 4.5 to the x equals the log of 4. Exponent comes down. And then we would divide both sides by log of 4.5. So whichever route you go, it's the same answer every single time. Now we're going to look at logarithmic equations. But before we do, I just want to bring something to our attention. So let's review. If I have log base 2 of 8, remember that's asking what exponent 2 has to go to get to 8. Well, that's easy. That's a 3. What about log base 2 of 1 over 8? Well, that was easy. That's a negative 3. Log base 2 of negative 8. Is there any exponent that I can put 2 to the power of, and get a negative 8? No, there is not. What about to get a 0? No, because negative numbers can be fractions. They get smaller and smaller, but they never actually equal 0. So remember the domain of our logarithmic equations. The argument, or the x value, so this is called the argument. The argument must be greater than 0. So there is a chance that we get that extraneous solution. An extraneous solution, remember, that's when you get it correctly, doing correct math, correct algebra, but when you plug it back in, it doesn't work. So no answers are going to be anything that if you plug it back in, you get a negative or 0. Those are going to be bad answers. So sometimes you'll actually have to sit there and plug it in, and sometimes you can look at them and really tell what you're going to get. Okay, so there were two cases with exponentials, matching bases or not matching bases. So let's look at that with logarithmics as well. We could have matching bases. So what if I have the log base 2 of 18 equals log base 2 of 2x? Kind of like on the exponentials, if we have matching bases, then the arguments are equal. Remember, the arguments are that input of the logarithm. So in other words, 18 must equal 2x, so x has to equal 9. If I plug that back in, 2 times 9 is 18. Neither of the arguments are negative, and neither of them are 0, so I'm okay. Now in this one, we want to get it to single logarithms that are equal. So that 2 is going to have to come in or condense before we start. So So log base 5 of x squared equals log base 5 of 9. Again, we have matching bases, so we can set them equal to each other, set the arguments equal to each other. So I get x squared equals 9. Remember, that's actually two answers. X equals positive or negative 3. Well, think back what we said about our arguments in the original statement. That x is an argument. It cannot be negative or 0. So the negative is a bad answer. The only good answer is x equals 3. Now, what if I had a situation where the bases were not matching? Or actually, these are when we have a single logarithm. This is, you won't see many where you have a different base on each side. Single logarithmic. So, let's see what I mean by that. Single logarithmic would be when I have something like, start real simple, log base 5 of x equals negative 3. Well, heck, we can rewrite that. Remember, the base of a logarithm becomes the base for an exponential, and the answer to a logarithm is the exponent. So that's 5 to the negative 3 equals x. That's x equals 1 over 5 cubed, or 1 over 125. Is that greater than 0? It is. We're good. Let me get another page. Maybe 4? Okay, sorry about that. On this next one, I said it should be a single logarithm, or one logarithm equals another logarithm. I have two logarithms on the same side with a single number on the right side. I wish somehow we knew how to turn those into one single logarithm. Oh, we do. We know how to condense. Condense means to turn two logarithms or multiple logarithms into the same one. Now, some of the properties of logarithms said if I add two logarithms, when I condense them, I'm actually going to multiply the arguments together. So what happens when I multiply those two arguments together? Well, I'm going to distribute. X times x is x squared. I'd have a negative 2x plus 3x is going to give me a 1x. And then a negative 6 equals 1. Now I have a single logarithm. I'm going to rewrite it. This is going to be the base for my exponent, and this would be the answer. So it would actually be okay to write it. X squared plus x minus 6 equals 4 to the first power. That's x squared plus x minus 6 equals 4. We have to set it equal to 0. And I made a mistake somewhere. This was supposed to factor. And it did not. So the teacher made a mistake somewhere. Let's try another one that actually works better. Sorry about that. Best laid plans never work like you want them to. Let's try, this one's even better. I've got something extra next to the logarithm. Well, we want to get a logarithm on one side, so we want to condense this, but I don't like that minus 5 being there. How can I get rid of it? Oh, let's just add 5 to both sides. When I condense those together, they're going to multiply. So x times x minus 5 is going to give me x squared minus 5x equals, and we added the 5 over here, so it equals 2. Now let's rewrite. So that's going to be 6 squared equals x squared minus 5x. That's really a 36. Set everything equal to 0, so subtract the 36 from both sides. And now let's try to factor. I think this one factors a little bit nicer. I'll do the hard part, x and x. What multiplies to be a negative 36 but adds to be a negative 5? Well, that's going to be a negative 9 and a positive 4. So my two possible answers are 9 or a negative 4. Let's see what happens when I check each of those in the original equation. When I plug in 9, that's positive argument. 9 minus 5 is still positive. This one works. What about the negative 4? It fails already, because that argument cannot be negative. That's a bad solution. That's an extraneous solution.